All right, let's go ahead and get started. Thank you once again for joining us this afternoon. Hopefully, it's a lunch break well used or it's some useful information. My name is Arvind Krishnan, and I work out of the Dallas office as an applications engineer with a focus on simulation and 3D printing. Today, we're going to look at some tips and tricks using flow simulation. A couple of housekeeping items. This webinar, the recording will be available on YouTube in our YouTube page, that is youtube.com/GoEngineer, and in maybe a couple of days. So let's go ahead and get started. First off, the outline for today. We can do a wide range of topics in terms of tips and tricks. We're going to narrow down to three things. One is preparing your model for analysis, meshing with SOLIDWORKS Flow Simulation, and troubleshooting. We'll look at some common error messages and see how what can be done to resolve them. So going ahead and getting started. Let's start with preparing for analysis. Spending some time on the front end of your analysis to prepare your model for it can result in huge time savings on the meshing capabilities and on the computation time. So a couple of things that can be done is you can simplify your geometry and remove things from your model that do not affect the actual flow or the dynamics of the flow. So if there are some fillets that don't actually affect the flow, or there are nuts and bolts, you can potentially create another configuration to ensure and have one just for analysis so that your model is a slightly simplified version and you can save time on the analysis. Sometimes it might be necessary to add geometry to mimic the flow condition. Imagine you have a truck as shown on the display, and you can do an external analysis on a truck to simulate the flow of the velocity profile around it, look at the drag force, things like that. But you may want to do some wind tunnel testing on it, and sometimes it might be required to simulate the actual shape of a wind tunnel to get an accurate description of how the testing data is going to look like. Quickly switching to SOLIDWORKS. Here is the truck that we spoke about, and we're looking at a velocity distribution of it. Once again, if we wanted to do some wind tunnel testing, so first off, here we're looking at what's called an external analysis. And in an external analysis, you have a computation domain, which is a cuboid in shape, and it goes around the truck. Now, if you wanted to simulate a different shape for the external analysis that goes around it, like a wind tunnel, you might want to define that shape, surround it with lids, and then do an internal analysis. I know that some of the other software out there require an outer bounding box for an external analysis as well. In this case, a computation domain is automatically defined and can be moved around based on your preferences. I'm going to quickly switch to an internal analysis. And like we spoke about the wind tunnel, in this case, we've modeled the wind tunnel and we've included a couple of lids on the front end and the back end. And let me go ahead and load up some results. So the conditions for the internal analysis, I have an inlet velocity that is similar to the external analysis that I did before. So the speed of the wind going across the face of the truck is still the same. Once again, loading up some results, and the results look slightly different owing to the slightly smaller size of the wind tunnel. So you can look at some of these geometry changes and effects of them by doing an internal analysis, which might need adding geometry to your simulation. All right. Moving on. Next up, let's talk about lids. First off, lids are needed. First off, an internal analysis needs a closed internal domain where the fluid can enter and exit the system. Sometimes, let's say you're a company that's designing pipes, you would not necessarily close the entry and the exit points of the pipe. But when you're doing an analysis, you need a closed region where the fluid can flow in and out of. Hence, you need to create lids to close it. Just a couple of quick tips about using lids. It's recommended to make sure that if you're in an assembly, that you have the lids as fixed. We've seen times before where a second user comes in and moves a lid by mistake and then saves the model, and then the analysis is now different, or the geometry is now different for the analysis as compared to what the original user intended it for. The other one is we would recommend saving the lids internally in the assembly itself as compared to a separate file. Once again, if you have multiple users, it helps in housekeeping. You might want to have the lids colored differently because that way it's easier for selection purposes. A lid is not required for external analysis. So let's go ahead and look at lids in SOLIDWORKS Flow Simulation. I'm going to quickly pull up a different model. So in this specific valve model, I want to point out a couple of things. First off, it's open on the sides. So to create a lid, Flow Simulation has a create lids option on the very top left. Let's go ahead and click on it. And this has you select a planar face with the opening. So if I go ahead and select this face, it's going to look at the different openings in that face and apply a small cylindrical lid that closes that face out. You can see that it's applied some on the outer faces as well, which is not needed. We can go ahead and delete those. But the important thing is it goes ahead and creates a lid where it closes the opening so that your model is now ready for analysis. I'm going to go ahead and cancel this. The second thing I want to talk about lids, let's go ahead and just look at a cut plot, a section view. And I want to talk about this opening on the very top. If you intend to use this opening to define a boundary condition for your internal analysis, a small amount of post-processing is needed because without the lid that's been created here, there is a curved opening and all lids or all boundary conditions must be applied on a planar face. So in this case, because this face was curved on the very top, a lid was created manually where you can go in, apply or define some geometry to make sure that that's closed. Typically, it's recommended to have a very small extrusion on the very top so that the actual dynamics of your flow is not much different as compared to the initial shape that's been defined. So that's talking about lids. Once again, you don't have to use the lid command to define lids. There's actually a lot of documentation out there which recommends modeling the lid yourself and gives detailed recommendations on how to do that as well. Moving on, let's talk about leak tracker. Let's say you are designing some components using sheet metal and there's some gaps in the bend radius or there are some gaps in the corners. Sometimes these gaps are really small and minute and it's hard to find out where the leak is. But flow simulation needs an enclosed region if you're doing an internal analysis, to define the fluid behavior inside the geometry. To help with this, Flow Simulation has what's called a leak tracker. Let's go ahead and look at this option. So once again, inside the Flow Simulation add-in, you have, I'm going to go ahead and turn off the section view. You have what's called a check geometry option. We're going to go ahead and switch to internal analysis and hit the check button. So it's basically going in and seeing if there's a defined internal region which is completely enclosed where some fluid can come in and come out. So, and here it tells you that the status of this has failed because it's a non-watertight model. Okay, so the actual fluid volume is equal to 0. Inside this window, you have a leak tracking option. Let's go ahead and click it. This lets you select an external face and an internal face. And once you select those two and hit find connection, it's going to find a way where it can just connect those two, and that's going to help you find out where the leak is. So for example, in this case, it's gone in and shown that this particular region, there's a leak here. So this means this is what tells me that there's an opening here that hasn't been closed, and I can use the lids option to close this opening to then run a simulation. You might want to double check the check geometry option after, so to see if there are any other leaks as well. All right, so this sums up the first section, which is preparing your model for analysis. Once again, just to sum up, simple changes that are made in the geometry can help greatly reduce the mesh size. It can help improve the reduce the computation time, and in some cases may also help improve the accuracy of your analysis compared to testing data. So you might need to add or subtract geometry specifically for analysis purposes. Moving on to the next segment, let's talk about meshing. Honestly, we can do an entire webinar on meshing, but here we're going to focus on a couple of key features. The main, once again, a lot of what we've seen through tech support cases is people using just one global mesh size to mesh the entire model. So if they feel like the analysis is not accurate enough, they just bump up the global mesh size a couple of slots to the right and get to finer mesh in the overall model, and then run the analysis again. So what is recommended is to use a local mesh and have a finer mesh in the regions that are critical to the analysis. So we're going to do a couple of tips on meshing and look at how we can use some of the local mesh options. The first one is a feature that was introduced in 2016 called an Equidistant Mesh. So let's quickly switch to SOLIDWORKS. I'm going to open up this airfoil model, and here is an equidistant mesh. So as you can see, you have your model, and then you have one layer of fine mesh around the model. There's a second layer that is relatively coarser, but still finer than the global size. And then you have the global coarse mesh itself. If the dynamics of the flow is important around the design of your part, right around the design of your part, then it is advisable to use an equidistant mesh to accurately simulate its behavior. To do this, you would right click on mesh and go to insert local mesh. Since I've defined one, I'm going to go ahead and look at the properties selected. You select a bunch of faces around which you want an equidistant mesh. Then you define the number of layers. So in this case, we have 2 layers. And so that's why the number of shells say 2. And then you define the distance. So here's the offset of the first layer from the faces selected, and then you have the second layer from the faces selected. So using these options, you can define a mesh that's a lot finer close to a specific face, and it becomes coarser as you go away, and then finally it gets to the global size. Another option is to define a region that needs a finer mesh. So we looked at the truck example before, and we're going to stick with this airfoil model, but let's go ahead and look at that local mesh one more time. This time we're going to switch to a region. What this does, it helps you define a region that needs a finer mesh. So this region may not have any geometry, but we know that, let's say behind a truck, there's some amount of low velocity or vortex, and defining that region is going to help you specify a finer mesh size for just that one region. You have the option of specifying a cuboid, a cylinder, or a sphere. Specify the X, Y, and Z of, or the minimum and maximum of them. You can do a sphere where you specify the coordinates and then the radius. So this gives you the options required to define a mesh in a finer region and specify what the mesh control is going to be. Now, sometimes these three shapes may not be enough, in which case you can model a solid geometry and specify that as a region. Just make sure not to include the solid geometry in your flow simulation model. You can remove that from the component control. All right. So once again, wrapping up in meshing, it is always recommended to have a local mesh with a smaller size defined for the critical areas, but keep the coarse mesh size for the other regions that are not that important. And this will help exponentially reduce your solve time, but at the same time give you accurate results for your models. Moving on to troubleshooting. Let's say you go ahead and hit that run button. Once you set up the analysis, you set up the pre-processing, you set up your boundary conditions, and then you hit run, and this solver window pops up. Now, any CFD analysis runs through multiple iterations where it tries to converge on a solution, and once it converges on certain parameters that are important to you, called goals, it will go ahead and stop continuing to solve. Now, what this means is this solver window gives you regular updates on what some of those parameters mean. It also tells you what the total number of cells are, what iteration number you are in, when did the last iteration finish, so that you get some idea of how long each iteration is taking. It also tells you warning messages. For example, one of the common ones is a vortex crosses the pressure opening. Let's go ahead and switch to SOLIDWORKS and look at a little bit more about what this means. Find a inlet volume flow from one end and a pressure condition on the other end. If you go ahead and look at the fluid behavior, you can see that the majority of the fluid goes out from this pressure condition through the middle. Now, when you define an environmental boundary condition, if the pressure is more on the inside as compared to on that lid, you're going to see fluid flow out. Whereas if the opposite is true, you're going to see some amount of fluid flow back in. And that's what's happening in some of these regions on the outside, where you see that the pressure is lower on the inside, and hence, because the environmental pressure is higher, the fluid is flowing in. Now, in some cases, the amount of fluid flowing back in is extremely small or is very minute, and it doesn't affect the accuracy of your analysis. In some other cases like this, you might want a larger pipe or a larger section of your geometry modeled for the analysis, or you might want to include a reservoir of fluid to understand the behavior of what happens after this region. In this case, we're going to go ahead and activate a slightly longer tube, and I'm going to go ahead and load up the results for the same setup, but for a longer tube. And let's go ahead and play the animation for the flow trajectory lines. What you're going to notice is there is a vortex in this region, and the fluid flows from the outside to get to the exit. What this means is, because of this region having a vortex, there was some fluid coming back in, and this behavior can only be accurately represented when you have a larger tube. All right, moving on. A troubleshooting message that often pops up is that the solver abnormally terminated. Now, there's multiple reasons for why this happens. One of them is, and let's go ahead and look through a few of them. So the first one could be because the lids were not created properly. If you look at the image on the left, the lid was manually created and the extrusion was outside. This means at the interface of the ID of that tube, the lid, there's only an edge of the lid that's in contact with it. This could cause problems when trying to mesh it and solve it, which might lead to the solver abnormally terminated error message. On the right side, we have a lid which actually goes slightly inward, and hence you have the face of the lid in contact with the ID of the tube. This is the correct way to create contact. This is the correct way to create a lid and get the meshing to work. Another reason why the solver might sometimes abnormally terminate is if you have multiple fluids and the concentrations of the different fluids are not adding up to 1. This initial concentration needs to always add up to 1. So let's say you're using 2 or 3 different fluids as shown in this screenshot. You might want to make sure that all of them adds up to 1. So in this case, 0.5, 0.2, 0.3 is 100% for either the mass fraction or the volume fraction. Custom fluids. Anytime you are using a custom liquid or gas or non-Newtonian fluid, and if you get the warning message about the solver abnormally terminated, it's always recommended to switch to a predefined material from the engineering database or a predefined fluid and see if that solves the problem. If it does, then in most cases, the custom fluid properties are the ones that are creating the problem. Oftentimes, this is because of incorrect units. So make sure you always check units and make sure you're using the correct units, especially for properties like viscosity and conductivity. This is very important for if these values are not correct, it creates problems in the solver. So it's important to check these values. Also, make sure that you don't have any non-zero values for these property numbers. Another thing that I've seen in the past is there was one case where we were using water as our fluid, but the temperature of the model was all the way up to 330 Fahrenheit. And based on the appropriate pressure conditions, the water might be in a gaseous form in this stage. So it might have been steam or water vapor. And the physics of the fluid that was initially included was not accurate at 300. The modeling of that behavior is not accurate at such high temperatures, and that might be one reason why the solver might terminate. Moving on. If you're using a non-Newtonian fluid and you're using a custom fluid, always make sure that you have maximum and minimum viscosity bounds set up for it. So that could be another reason why the solver would abnormally terminate. One more reason, if you ever see that message, try to include at least 5 cells across a flow passage. This might increase the computation time, but it results in a more accurate solution. Sometimes we've seen one cell have an extremely high velocity and then an adjacent cell have a really low velocity, and that distinction is way too much because the cell size is really big, and that results in the solver terminating. So those are a few cases and some of the options that will help troubleshoot your analysis. Moving on, sometimes a steady state solution is not available. In this case, we have a cylinder with a high fluid flow around it. And if you look at this flow, there is not one steady state solution because of a phenomenon called vortex shredding. So what's happening is at a given point of time, you have a solution available, but there is no steady state solution irrespective of time, because this alternative pattern in its behavior constantly takes place based on the distribution in the previous time step. So if you're not seeing convergence of your solution, one reason might be to switch to a transient analysis for a relatively longer length of time to see if you reach convergence based on a transient analysis. This concludes this webinar. Once again, the main 3 topics were preparing your model for analysis and spending some time in the front end so that the computation time and mesh size is relatively lower. We looked at some local mesh tips and tricks where you can specify a smaller size for a given region or around a part or a model and get a smaller size for the mesh in that one region, but still have it relatively coarse overall. And finally, we looked at some common error messages that might pop up and looked at some potential solutions for it. Once again, my name is Arvind Krishnan. If you have any questions or would like some additional information on what we spoke about today, feel free to contact me and I'll be glad to help you out.